The section 4.4 is on complex numbers. This will mostly be new to you today. So pay close attention. Make sure you take good notes. We're going to try to move relatively quickly as well. Now, here's what you need to know about complex numbers. Earlier in chapter 1 this year, we looked at the set of all real numbers. If you recall, it was a little something like that. This is our Venn diagram. R was real numbers. I is irrational numbers. Q stands for stop taking pictures. You're gonna in a minute. I'm gonna put stop taking pictures.
We already have them.
Stop taking pictures. Stop taking pictures. I will tell you when to take a picture. Real numbers are made up of rational and irrational. Within rational numbers we have integers, whole numbers, and natural numbers. That's not new, you've already had that. Okay? Complex numbers consist of all real numbers, but they also consist of imaginary numbers. The complex number system looks like that. Now you can take a picture. Basically, the set of all real numbers over here and imaginary numbers. Put those together and you get the set of complex numbers.
Is that in the book, the imaginary?
That is not in the book. I made it myself. Now, let's talk about what imaginary numbers actually are, and yes, they are a figment of our imaginations. Here's how it works. Okay, I is the imaginary number. Normally, you would write this as a script lowercase r. This program will not allow me to do that. So as you are writing the imaginary number I in your notes, please write it as a script lowercase I. Normally, I would write it like, like that. Script I. Okay? So every time I use the I from my keyboard, yep, make a little script I instead. Okay? Here's what it equals. I equals the square root of negative 1. Yes. Okay, square root of negative 1. We'll get into where that comes from and why it's important here in a little bit. But that is the imaginary number. Okay? All complex numbers can be written in the form a plus bi. Where a is the real part, bi is the imaginary part. So in fact, every real number could also be written in this form. It just so happens that b is 0 every time you look at a real number. The imaginary part isn't there because b equals 0. For that matter, you can write imaginary numbers without the real part. If a was 0, you would just have an imaginary number. Put them together, and you get a complex number. Real and imaginary combined together is the complex number. Okay? Let's get into it a little bit more. Let's look at an example of a problem we're talking about. Here's a type of thing where the imaginary numbers are going to come into play. When I look at the square root of a negative number, right? Most of your calculators, if you tried to punch that in, it'll give you an error. Because there is no number that you can multiply by itself that will equal negative 16, let alone a negative number, period, right? If I take a positive times a positive, I get a positive. If I take a negative times a negative, I get a positive. So this is why we have imaginary numbers. I can't take a number by itself and then it'll be equal to a negative. So some old dead mathematician somewhere along the way said, but if I could just deal with that negative, I'd be fine. Because you all know what the square root of 16 is, right? 4, okay? So here's what he did. They invented the imaginary number. And so instead, we started working at radicals like this. And whenever, if you remember your radical properties, if you can find a product of two numbers, you can place them, you can break that that number up into its factors and multiply underneath the radical. And if you remember your properties, then from there I can actually separate that into two different radicals. And so now we can find the square root of 16, right? And the square root of negative 1 we just learned today was I. When I simplify the square root of negative 16, it actually equals 4I. So now that we have complex number system in our life, we can actually do something besides write error, no solution, whatever. We can actually simplify. Now, I think some of your calculators would do that for you, and you probably punched it in, and you got something like this, and you didn't know what it meant. Okay, from this point forward, you're supposed to know what it means. Okay, any questions? Let's look at that one. So we've got this negative here. That's going to be an issue for us. That's where the I is going to come into play. 27, is that a perfect square?
No.
Is there any factor of 27 that is?
No.
Yes.
9. 9 goes into 27. That's a perfect square. So I could break this down this way.
I can understand what you're asking.
I could break those down. The square root of 9 is 3. Square root of negative 1 is I. So here's what's my next move. Okay, so I have 3 times square root of 3 times I. And when we actually write it, so here's where it's gonna seem like I'm contradicting myself. But let me show you why I'm not. Okay? When I rearrange this and write it, whenever you have numbers outside of a radical, they all go in the front usually when we deal with radicals, right? Look like this, 3I root 3. Here's the one thing I need you to kind of keep in mind that's going to sound contradictory. If they insist, and it'll say in the directions, make sure that it's in complex number form or a plus bi form. Here's the time when you wouldn't do it like that. You'd have 3 root 3, because that's all the real number part, right? That's the b. And then I have the I. Okay, so if they ask for it in a plus bi form, you'd actually have to switch it around like this. The reason why I've got this little extra space in here, and the reason why we typically write everything in front of the radical, is that oftentimes the radical sign can leak over here, or this can kind of get stuck in over here, and there's the possibility of thinking that that number over here is actually under the radical, and by putting it out in front up here, you can't mistake that it's underneath the radical because it's clearly not. So the directions will tell you. Typically, you can leave it like this and that's fine. If it asks for it to be in a plus bi form, you'd actually probably also put the 0 in front. Okay? If it asks for a plus bi form. Okay? Questions? Just know the difference. Typically, we're not going to use this unless it absolutely asks for it. Yeah?
So what would the name of like form, the first one be 3I, radical 3?
Yeah, it doesn't really have a, it's just simplified form. Okay? Simplified, it's really simplified radical form. Okay? Alright, questions so far? So, we're going to look at I raised to a bunch of different powers, and I'm going to show you some patterns and key points that are going to make this important. Okay? So we know that I equals the square root of negative 1. Let's look at I squared. Here's where the power of imaginary numbers comes into play. And this is what, to me, makes it fascinating. All right? If I raise square root of negative 1 to the second power, okay? Because that's what I squared really is, right? What is the relationship between the square root and a squaring? What is the relationship? They cancel. What is that known as? They are what? No.
I tried.
Inverses. Okay? Square root and squaring are inverses, which is the reason why they cancel out. Okay? So the reason that they cancel out is that they are inverses. So if I take the square root of negative 1 squared, that actually equals negative 1. So think about this for a second, and here's to me where it's powerful, right? An imaginary number, a number that actually doesn't exist except for in our imagination, when squared, becomes a real number. Okay? There are going to be other circumstances where I can have imaginary numbers combined together to equal a real number. And we're going to look at some of those today. Okay? So that's the first thing. This one is huge. I squared equals negative 1. You don't need to go through this process every time. This is just me showing you that it's equal. But from this point forward, when you see I squared, you immediately need to think negative 1 every time. I squared equals negative 1, and don't lose that. Hold on to that forever. Okay? Let's look at the next one, I to the third. So, this is the square root of negative 1 times I. Well, I squared is what? Negative 1. This is negative 1 times I. So, I to the third is actually negative I. In your homework today? Well, you could say that about lots of things in math. The last one we really need to look at is I to the fourth. Okay, I to the fourth is it 1? Why do you say it's 1?
Because it's I squared times I squared.
I squared times I squared, yep.
Negative 1.
So that's negative 1 times negative 1, which is 1. Okay, now here's what happens. If I kept going, I to the fifth would be I. Okay? I to the sixth. So this pattern, it goes in groups of 4. I, negative 1, negative I, 1. Now, what we're going to do is actually simplify some other problems. And the key thing is, since I to the fourth is 1, all you need to do is figure out how many I to the fourths go into each particular term. You'll see what I mean here in a sec. We're going to simplify these 3 problems. What we need to figure out is how many i's to the fourths go into each of these. And the first one's pretty easy, right? 4 goes into 6 one time, and then there's how many left over? 2. So this is pretty easy. I to the fourth times I squared. Well, what's I to the fourth? What's I squared? So I to the actually equals negative 1. If I wanted to have written it this way, I could have said I to the fourth to the first. Right? Because that is just I to the fourth. 4 goes into 6 one time. So I to the 35th, let's look at that one. How many times does 4 go into 35?
8.
How many left over?
3.
Okay, so here's the way to think about this. This is I to the fourth to the, how many times does it go into 35? 8. Right? Times, how many left over? You with me?
Yes.
Okay, so what does this equal? See, all of this right here, what's all of this?
1.
1. What is I to the third?
Negative I.
Negative I. Okay? Do the last one. Do the last one. 2 options here. Okay? You can either write out this part here. You don't have to necessarily write it out. Listen up, please.
I think I got the answer.
The remainder is the key. So look, 6 divided by 4, remainder was 2, so I'm looking at I squared. 35 divided by 4, the remainder was 3, so I'm looking at I to the third. 81 divided by 4, what's that? 20, what's the remainder? So what's my answer going to be? Well, yes, but we don't write that. So it's just going to be I, right? I to the fourth to the 20th. So this is just I. We don't actually write the square root of negative 1. Okay? So in reality here, the trick is when you simplify these over here, you're going to get one of those answers over there. Okay? And the trick is the remainder, whatever the power is divided by 4, that remainder is going to tell you what the solution is.
Is it gonna get harder?
Yes, we have way more.
Can it not get harder?
The next thing, operations with complex numbers. So here's the thing. The raising I to different powers is important, but more importantly is we can use operations, addition, subtraction, multiplication, division, with complex numbers. Just the same way that we could with real numbers. The algorithms are gonna be the same, the processes are gonna be the same, however, there's gonna be a slight difference. First of all, you need to treat I like it's a variable. I is not a variable. It represents the square root of -1. But when we use it to perform addition, subtraction, multiplication, and division, you treat it like it is a variable. And all the processes that you know how to use for algebraic expressions will apply. Okay? It just so happens it's a complex number and not a variable. So I'm going to give you 3 problems right off the bat. An addition, a subtraction, a multiplication. Division is a little bit different. It's its own little thing. So I'm going to give you that one last, and we'll do that on a separate slide. So I'm going to give you 3 problems, all involving the same 2 complex numbers. So part A, this is addition. I'm adding -2 plus 5i to 1 minus 7i. So here's an addition problem. Same 2 complex numbers subtracting, same 2 complex numbers being multiplied together. Everything you know about algebraic expressions, combining like terms, and all that stuff applies to this. So, do these 3 problems. One recommendation I can give you, okay? Some of you are getting really hung up on this whole abstract concept of imaginary numbers. Like, get past that. The fact is, there's not a lot, besides the fact that it's an imaginary number, there's not a lot that's actually new. Okay? While there are some new concepts, that abstract concept that is floating above your brain right now, that you're struggling with, you need to let go of. Because the processes, the algorithms, the properties, all that stuff that you already know, you get to apply to a concept that is really very abstract. But if you continue to focus on the abstractness, it's going to distract you from what it is you're capable of demonstrating, okay? So don't get hung up on it. For this problem, okay, I'm looking for a number to be in front of this parenthesis, and since there is not a number there, there's nothing to distribute, okay? So really, for this problem, all you have to do is drop the parentheses and combine like terms. For question B, it's a little bit different. This minus has to be distributed, right? So I have to distribute it to each of those, and then I have to FOIL here. So here's your second step, and all 3 should be. So notice here in part A, all I did was drop the parentheses. For part B, I basically switched the signs of everything inside. So this goes to -1 plus 7i, and then out here I FOILed. How many had step 2 right in all 3 of them? Okay, good. Now it's just a matter for part A of combining like terms, part B combining like terms, and my guess is part C combining like terms, except what did I tell you about I squared earlier?
It equals -1.
Equals -1. So every time you see it I squared, you need to replace it with -1 every single time. Your final answer cannot have an I squared in it because we know what I squared is. So you have to replace that. So here's what your next will look like. Okay? So on the first one, -2 plus 1 is -1. 5 minus 7 is -2i. How many had A right? Raise your hand. Okay? B, -3, so -2 minus 1. 5 plus 7. How many had B correct as well? Alright, so notice what happened in C. Alright, I combined the 14i and the 5i. That gave me 19i. I replaced this minus 35i squared Since this is -1 times a negative will be plus. Now I can go one more step on this part C, right? What are the like terms that I can still combine? -2 and 35, which is 33. So my answer for C is 33 plus 19i. Now, those of you who had 19i plus 33, that is not complex number form, right? Complex number is the real part, then the imaginary part. So 33 plus 19i is the way that it needs to be written, okay? So just make sure that you get it flipped around and you're good to go. Any questions about any of those things? Okay, so let's understand something. Again, when I said treat I like it's a variable, everything here, if I would have replaced all the i's with x's, you would have basically got the same thing over here and over here. The only difference is this I squared. Everything else is exactly the same as if I was a variable. No algorithm different, no process different. The only substitution that took place that was different was this I squared, okay? Question. Let's get to division. Here is division. Here is an example of a division problem. I realize it looks like a fraction, but let's face it, fractions are just division. So, think back to when you worked with radicals for the first time. Having an I in the denominator means I have a radical in a denominator. Okay? You can't have radicals in denominators. What you did in the past was called rationalize a denominator. Okay? So no radicals in denominators. We don't want to have that. In the past, when you had a binomial in a denominator with a radical, you had to multiply by the conjugate. Maybe you remember that term. When it comes to imaginary numbers and complex numbers, you are still going to multiply by a conjugate, but it has a special name. It is called a complex conjugate. And if you remember what a conjugate is, it's the exact same binomial, except the middle sign is changed. Okay? So my conjugate for 3 plus 5i is just going to be 3 minus 5i. That's the conjugate. You just change the middle sign. You remember that? How many remember doing that before? Changing that middle sign, okay? Now, if I multiply the bottom by 3 minus 5i, what else do I have to do? Multiply the top. Does anybody know why we have to do that, the top and bottom like that? Okay, there was a bunch of words that you all said at the same time that I could not understand. Why? Why does it make it stay equal? Yeah. But why? Yeah. Right. This is equal to 1. So if I multiply an entire expression by 1, its value doesn't change. We're going to change the way it looks, but when I multiply top and bottom by the same thing, or I'm really multiplying by 1, which means the value of this isn't going to change. We're just going to change how it looks. So, now that we know what we're supposed to do, you go ahead and do it. So first of all, when you multiply everything out, take a look at what I have. Hopefully that's what you also have. Okay? Now, here's the thing. Here's the thing on the bottom. Here's the thing on the bottom. The reason conjugates work. Think about factoring. Okay? Think about how we just got done doing some factoring. Okay? And think about, in particular, a difference of squares. This looks like a difference of squares factored, right? The fronts are the same, the backs are the same, and the middles are, the signs are different. So notice here that these middle terms are going to cancel out, and I'm going to have a perfect square and a perfect square. Okay? That's what's supposed to happen. When you multiply by the conjugate, the middle two terms are supposed to drop out. So if that doesn't happen for you, you did something wrong. The most common mistake that people make with the conjugate is they forget to change the sign. And so I'll see people doing, for example, 3 plus 5i times 3 plus 5i, and the middle terms don't drop out, which means you picked the wrong conjugate. So make sure you keep an eye on that. Now, again, every time I see an I squared, you can think -1. Okay? And so what I just did here, -6i plus 10 became -10 because I squared is -1. The 15i's minus plus cancel out. -25 times I squared, again, that's -1 times -25. So that's what you get for there. How many had that? Okay, good. One more step before we're going to separate it into its own fractions. So here's where I'm at right now. -6i minus 10 over 34. Okay, I'm not quite there yet, so relax. All right. Because here what you have to do is put it in a plus bi form and reduce. Clearly it's not in that form right now. So here's what I'm going to do. When you have a binomial or any type of polynomial on top of a fraction, and notice here the denominator is now a real number. I no longer have radicals in the denominator, and that's what's supposed to happen when you multiply by the conjugate. So when I separate the top into its own fractions, everything on top goes over 34. Okay, and I'm going to flip it around to have the I come second. So that's what it kind of looks like right now. And there's one other thing that I want to point out. So again, it's the -10 over 34 and the -6. Now notice how I slid the I to the side instead of keeping it up here with the 6. In order to be in a plus bi form, this whole fraction here is b. Okay? So I separate the I from it so that I can identify clearly what b is. The only thing left I need to do, and then this is a, the only thing left I need to do is reduce. So what goes into -10 and 34? What else goes into 6 and 34? 2. So I can reduce both by 2. So I get -5/17 minus 3/17 I, and that is my final answer. Okay? When you divide with complex numbers, it's often messy. And it will often lead you to fractions like this. Don't be surprised. Okay? So let's just kind of wrap it all together. Okay? Imaginary numbers, I equals the square root of -1. You need to know that pattern. I squared is -1. I to the third is -I. And I to the fourth is 1. Adding, subtracting, multiplying, dividing. Operations with complex numbers. Things that you have done before. Just all kind of being combined together. Any questions?